So good morning, everyone. Dima, if you're willing, would you try to go ahead and share your screen just so we remove the possibility of one technical problem?
Yes, let me try this.
Perfect. Thank you.
Mhm.
Evan, this is Takao Sakaguchi, the chair of the Nuclear Physics Committee. I'm going to record this seminars, and as well as this seminar is now live streamed.
Yes.
Yeah.
I will announce that it's recorded. Probably people will see the message anyway, but
Okay.
unless I forget, I'll announce it also. Thank you.
You're welcome.
Okay, good morning, everyone. We'll go ahead and get started more or less on time since I think we may be a little tight for time. So my name is Evan Finch from Southern Connecticut State University. I'm a member of the STAR collaboration. So today is very exciting. We'll hear the results from STAR on their blind analysis, looking for evidence of the chiral magnetic effect by comparing the charge separation signal and collisions of two nuclear isobar systems. So it's the result of a tremendous amount of work by many people. So today's seminar will be in three parts. First, Dmitry Karzaev will give a 15-minute overview of the chiral magnetic effect and its significance. Then Jim Drachenberg from STAR will give us a 10-minute overview of STAR's blind analysis procedure. And finally, Jamie Dunlop, also of STAR, will have 25 minutes to walk us through the results of STAR's analysis. So I should note, you probably saw the message, but today's seminar is being recorded and live streamed. And we'd like to defer all questions for any of the speakers until after the end of Jamie's talk. And for each speaker, I'll try to politely interrupt and give you a 2-minute warning for time's sake. So I apologize in advance for that interruption. Okay, so first, it's a great pleasure to introduce Dmitry Karzaev. Dima is a distinguished professor and director of the Center for Nuclear Theory at Stony Brook. He's also a senior scientist in the nuclear theory group at BNL. So in the interest of brevity, I'll just say that Dima's expertise spans a wide range of topics. And among those, for the last 20 years or so, has been his work on local symmetry violation in QCD and the chiral magnetic effect. So he will give us a theoretical overview. So thank you, Dima. Whenever you're ready, please go ahead.
Thank you very much, Evan. It's a real honor for me to give a very brief theory introduction to this long anticipated announcement of STAR results. And I'm very grateful to the collaboration for giving me this opportunity. I know it's a result of a great amount of work by many people over many years. I do not know what these results are going to be, but nevertheless, I'm quite sure that they will inform the future experimental and theoretical work, and will definitely represent a milestone in our understanding of nature. So what is the chiral magnetic effect, and why do we believe that it is important for understanding the universe? So
Dima, you just became muted. Let me try to undo that.
Yes, chirality is a ubiquitous concept in modern science, from particle physics to cosmology. And in subatomic world, chirality refers to fermions, and depending on the projection of the spin on momentum of the fermion, fermions can be right-handed or left-handed. So fermions also interact with gauge fields, and gauge fields have chirality as well. So for example, they can form knots of magnetic flux in magnetohydrodynamics, and knots can be chiral objects, and their chirality is classified by Chern-Simons number, which is topological invariant. Charged chiral fermions interact with gauge fields, and therefore chirality can be transferred from fermions to gauge field configurations through the so-called chiral anomaly. In the vacuum of standard model, we have an infinite amount of states which are characterized by different chiralities. And there are processes of reconnection when chirality of gauge field changes. And these processes in which chirality is changed are called instantons or spirons. So all of this has a huge significance for the existence of the physical world as we know it. And a long time ago, Sakharov formulated criteria for baryogenesis and pointed out that one needs baryon number violation, C and CP symmetries violation, and interactions out of thermal equilibrium for our world to exist, asymmetry between matter and antimatter. So within the standard model, baryon number violation happens when transition occurs between these generic vacuum states with different topology in electroweak sector of the standard model. So can we study these processes that believed to happen in the early universe in the lab? The answer, unfortunately, is no, because the temperature of electroweak phase transition is very high. The height of potential barrier is also very high, and so unfortunately they are impenetrable at present energies. However, we can study completely analogous processes in another non-abelian gauge theory of the standard model, which is quantum chromodynamics. The point is that the temperature of QCD phase transition is 1,000 times lower. QCD plasma is produced in the ongoing heavy ion experiments at RIC and LHC. And transitions which are accompanied by the change of chirality instead of baryon number violation. And the rapid expansion of produced plasma drives it out of thermal equilibrium. So analogs of Sakharov criteria are satisfied in heavy ion collisions. And in complete analogy, we can expect to see a substantial generation of net chirality of fluctuating sign in heavy ion collisions in analogy to the generation of matter, antimatter asymmetry in the early universe. So these transitions do happen in the vacuum. Numerous first principle work indicates that these transitions occur. However, they have never been detected directly in experiment. And so the question is it possible to directly observe this chirality change in transitions in experiments? So luckily, the answer to this is positive, but it's not easy. So topological transitions in QCD plasma change chirality of quarks. However, quarks are confined into hadrons, and their chirality cannot be directly detected in heavy ion experiments. And therefore, to observe this chirality change in transitions, we have to find a way to convert chirality of quarks into something observable. And so one way of doing it, and in fact the only way that we know at present, is to convert this chirality into electric dipole moment of the QCD plasma. And this requires an external magnetic field or an angular momentum. So the point is that if you have a net chirality of quarks generated in this topological transitions and quantified by the chiral chemical potential, then in the presence of a magnetic field, this chirality imbalance leads to electric current, and the electric current produces a fluctuating electric dipole moment of the hot QCD plasma. So the goal is to detect this in heavy ion collisions, and this is what STAR collaboration is after. So the necessary ingredient for this is to create a strong magnetic field, and fortunately, positively charged ions colliding at the speed of light produce extremely strong magnetic field, which is the strongest available in the laboratory. And this magnetic field rapidly decays, and the higher is the energy, the more rapid is this decay is. And this is why RIC has much more favorable conditions for observing CME than the LHC. So now, once we have this magnetic field and we have a chirality change in transition that generates a net chirality of quarks, this leads to electric current and to the electric dipole moment of the quark-gluon plasma, oriented out of reaction planning. So the problem is that unlike in weak interactions, where the sign of this electric dipole moment is fixed once and for all, in our case, it fluctuates, reflecting topological fluctuations in PCD, and therefore there are backgrounds to this observable. So this is a big difference of this observable from the classic parity violation in weak interactions. So this problem was recognized from the very beginning, and already in 2004, in a paper by Sergei Voloshin, he clearly understood the importance of this background and proposed a variable which would minimize the sensitivity to backgrounds. This was also recognized in the very first paper by the STAR collaboration. And since then, the fight with background was really the name of the game in this studies. So a very important idea by STAR collaboration members was to separate the signal from background by using collisions of the isobar pairs. The point here is that isobars are nuclei which have the same mass number and approximately the same size and shape. And since all known backgrounds are driven by geometry, this means that backgrounds would have to be the same in collisions of two isobar pairs. However, since the isobars have different electric charge, 40 and 44, this means that the magnetic field is different in these collisions. And since the signal that we are after is driven by a magnetic field, one expects to find a difference in the signal. And so now the very big question, and the question that we are all looking forward to hearing the answer to from STAR members, whether this difference is enough to observe the change in the signal. And so without further ado, I would like to give the floor to my STAR colleagues to tell us what the real answer is. Thank you.
Thank you, Dima, for that very thorough summary. So if you could stop sharing your screen, and we'll try to have Jim start sharing his. So thank you again to Dima, and we'll defer all the questions again for all the speakers until after Jamie's talk. So our next speaker is Jim Drachenberg from Abilene Christian University and a member of the STAR collaboration. So Jim's chief expertise lies in studies of the proton spin, but he's also served in STAR as chair of the committee that determined the blinding procedure that the CMA analyzers would follow, both to ensure integrity and quality of the blind analysis. So Jim, whenever you're ready, please take it away.
All right, just to check, Evan, can you hear me okay and see my screen?
Both.
Wonderful. Well, thank you, everyone. As Evan said, my name is Jim Drachenberg from Abilene Christian University, and I'm going to present the method that was used to perform the blind analysis of the STAR isobar data. I want to begin by talking about some of the important considerations that we made in developing this procedure. First of all, for STAR CME analyses, our analysts identified that it was critical for them to be able to account for things like time-dependent changes in the state of the detectors, and also identify and correct for anomalies in our set of 30-minute data acquisition runs. And so when we developed the procedure, we wanted to make sure that we enabled them to perform these tasks. In the end, we considered but shied away from selecting a blinding method that relied on randomizing certain variables. And our reason for that is because we did not want to inadvertently compromise the quality of the analysis. And just to provide a hypothetical example, if we had randomized the sign of reconstructed charged particle signals, that would have precluded our analysts from performing a charge-dependent correction of efficiencies if such a thing became necessary. What we settled on instead was a method that was really enabled because of the innovative running of RIC. So in 2018, our data taking frequently switched between ruthenium-ruthenium and zirconium-zirconium collisions. And so because we expected these collisions to have comparable behavior in a lot of ways, this opened up the possibility to blind the data by mixing or interleaving events across the two species. And so that is ultimately the direction we went for our blinding process. Now, we recognized that in order to collect the highest quality data we could, that we may need to allow certain non-analyst experts to have as much information as possible. So specifically, our star detector experts during the running of RIC and our calibration experts who are critical in ensuring the quality of the data. We wanted to make sure we allowed them to have as much information as possible, with the understanding, of course, they would be recused from performing a blind physics analysis. And then finally, we recognize the importance of selecting high quality data acquisition runs for our physics analyses very early on, and in particular, prior to mixing of events. Now, all of this work began as a result of the 2017 BNL Nuclear and Particle Physics Program Advisory Committee that recommended that our CME studies of the isobar data be done in a blind analysis framework. So we developed this procedure, which has been published in a manuscript in the journal Nuclear Science and Techniques, and it's a multi-step process. My subsequent slides will dive into some of the details of this, but just to give a broad kind of a bird's eye view perspective, this is a multi-step process. And it was developed and accepted by the collaboration early on in January 2018, well before data taking proceeded. In the initial steps, we perform some calibrations and quality assurance of these data acquisition runs, as well as a mock data challenge that serves as a sanity check of the method. In the first step of analyzing the data, our analysts analyze output files comprised of a mix of the two isobar species. It's at this stage that those time-dependent QA can be performed. In the second step is where the run-by-run assessment can be performed. At this step, the analysis code is frozen, and then those frozen codes are used to analyze the fully unblind data. Now, all of this is enabled because of the innovative running of RIC during 2018. The isobar species was switched each time the beam was inserted into the collider, which ran with a stable luminosity match between the species for very long, and by very, we mean 20-hour-long beam circulation times. And I really need to give some figures to illustrate this. The luminosity was adjusted and kept very level, as you can see here from the coincidence rate of this particular detector that optimized our rate of data collection, which is illustrated here by this figure. It's kept very high and very stable throughout that time period. At a rate that minimized the backgrounds that we can encounter in the associated systematic uncertainties. During this time, we tried to restrict the species-related information only to those who were necessary for successful data taking. And that included our calibration experts who really engaged the data quality assessment in real time of the data. As the data were being collected, that quality assessment was being performed. And so as we prepared for the analysis of the isobar data, as I mentioned, the calibrations and the run quality selection was carried out, but we also developed the software infrastructure needed to implement the procedures, and in particular, the specifics of the event mixing procedure and how to encrypt the data acquisition run numbers. We also identified other pieces of information that would need to be obfuscated or blinded in the data stream. Some of that's probably obvious, things like collision species, but others perhaps less so, things like the coincidence and background rates of certain detectors. These pieces of information that could potentially be used to tell the species apart in the fully unblind analysis become critical, actually, as ways of confirming that when we think we're looking at a ruthenium-ruthenium collision in the data stream, we can confirm that by looking at the data themselves. So this step even provided some benefit to us down the road. We also participated in what's called a mock data challenge, and this is really a sanity check of implementation of the procedure. What's done is that we take real data, gold data from the same 2018 run period, and we reconstruct that as though it were the blind isobar data. The analysts then can tune their codes on these mock data as they would in the actual isobar analysis. And here I show an example of a particular observable that's analyzed at each of the 3 stages in the process. And this gives us a check that the infrastructure works as we intended, that we blind the information we intend, that we don't blind information that we did not intend, that's critical to performing the analysis, even that the codes themselves run properly on the data structures, and that unblinding doesn't give us something that we don't expect. These are gold data, so unblinding really shouldn't change anything. This gives us a sanity check of each level of the procedure. At that point, we proceed to analyzing the blind isobar data themselves. And in this first step, what are provided are output files that mix across the 2 isobar species. Now, this procedure is encrypted, only 2 computing experts know what it is. But as much as possible, it reflects the time-dependent changes in the detector states and the run conditions that are critical, a critical piece of the CME physics analyses. So at this point, the analysis codes are tuned, that time-dependent QA is performed, and they're able to extract things like time-dependent spectra or identify time-dependent anomalies. Once the analysis is complete, the codes are frozen, they're committed to a repository where things can be documented and reviewed by the isobar paper review committee and ensure that what was intended to be done was in fact what was actually done. At that stage, then we proceed to step 2. And in step 2 of the process, analysts are given output files that blind the species but do not mix across different runs. So a given data file is going to contain events only from a particular isobar species that is blinded, but nevertheless gives us some intentionality about how we handle this. And so we limited the number of events in the data file so that you could not decipher the species just from a particular file. And furthermore, we restrict what can be changed in the frozen code. And this is specifically for those run-by-run corrections where we're identifying anomalies in a given run. Only those changes are allowed. So the analysts can identify additional bad runs using a predefined and frozen algorithm and target those for physics quantities that are relevant for their specific analyses. At this stage, just as in step 1, the codes are again reviewed, frozen, committed to the repository, and at that stage, the frozen codes can be used to run over the fully unblind data and the results produced. Now, we recognized that it's possible that mistakes happen, and we wanted to be deliberate about what we consider a mistake that can be fixed. What we mean by that are things like errors in arithmetic that obviously would have to be changed, and any unintentional departures from the procedure that was documented and approved prior to the unblinding of the data. And only those 2 things we determined would be allowed to be fixed. And so this method is a multi-step process. It is specifically tuned to allow for those critical pieces of the CME physics analyses that our analysts identified as being necessary. And I hope that you've also been able to see how development and implementation is a substantial and collective undertaking involving innovative running of the RIC machine, new software and computing infrastructure developed, and cooperation across multiple analysis groups, multiple physics working groups, multiple committees. And so I think it's appropriate that I end here by saying a special thank you to these myriad people who've been involved and supporting this effort from the very beginning. Thank you.
Thank you, Jim, for that nice, clear summary of STAR's procedure. So sort of on to the main event. So Jim, if you could stop sharing and we'll try to get Jamie's slides up. So our final speaker is Jamie Dunlop. So Jamie is the Associate Chair over Nuclear Physics at BNL and also a member of the STAR collaboration. And for this work from the beginning of the isobar analysis, Jamie has really functioned as a coordinator and as oversight of the 5 separate groups doing the analysis. And so Jamie has been chosen by STAR to summarize the results for us today. So Jamie, whenever you are ready, please take it away.
Thanks, Evan. Let's see. I'm gonna just get my pointer up. Why is this not working? Okay. Okay, it's a real honor to be giving this talk on behalf of the STAR collaboration. As Evan said, I'm giving this talk because I was the chair of the paper writing committee, or what we call the godparent committee on STAR. But this work in this paper that will be submitted today for publication, is a huge effort from the collaboration and from the operations team at RIC. So I'm going to order the talk. Let's see. I'm going to order the talk by the abstract of the paper. So let me just start with reading the first few sentences of the abstract. So the first sentence is the chiral magnetic effect is predicted to occur as a consequence of the local violation of parity and CP symmetries of the strong interaction. An experimental manifestation of the chiral magnetic effect involves a separation of positively and negatively charged hadrons along the direction of the magnetic field. Previous measurements of the CME-sensitive charge separation observables remain inconclusive because of large background components. And in order to better control the influence of signals and backgrounds, we embarked on a blind analysis of a large data sample from approximately 3.8 billion isobar collisions of ruthenium and zirconium at 200 GeV. Okay, so walking through a little bit of a history, I'll be showing many variables throughout the talk, but one of them, and probably the first variable, is this gamma correlator that Dima talked about earlier. So the chiral magnetic effect will lead to a charge imbalance along the magnetic field, and the magnetic field is aligned perpendicular to the second order reaction plane. But because the direction of that imbalance can change and fluctuate event by event and actually region by region inside the plasma, you need to correlate two particles with that reaction plane. And this gamma correlator was designed to measure this charge imbalance across the reaction plane. It was designed to be sensitive to the preferential emission of positively and negatively charged particles on opposite sides of the reaction plane. And the first measurements are shown here back in 2009. You can see that oppositely signed particles or oppositely charged particles have a positive value for this correlator. Same sign particles, or particles of the same charge, have a negative value for this correlator. But you can also see that it's imbalanced across zero, right? And so that's likely due to some charge independent backgrounds. So for the purposes of most of the rest of this talk, we take a difference in various variables. One of them is this gamma correlator between the opposite sign charge and the same sign charge, and we call that delta. So delta gamma. Now, there are also some numbers here. 112 means that inside the correlator, there's 1 phi for one particle of interest, one charged particle measured, 1 phi for another particle of interest, the other charged particle measured, and then 2 for the reaction plane. Other measurements put different numbers underneath the cosine in this mean. Okay, but it was pretty quickly realized after the first measurements that there are significant backgrounds such as flowing mesons or flowing clusters, flowing resonances, local momentum conservation. I think there are 60 citations in the paper talking about various types of backgrounds that can mimic the signal. There have been many methods that have come up with to try to separate the signal from the background. And here the isobar and the isobar collisions, as Dima said, the idea is to hold the background fixed, but modify the signal because the background is predominantly reacting to the total number of nucleons or the geometry of the collision, while the signal is reacting to the electromagnetic charge of the incoming nuclei, which change the magnetic fields, right? So you can do a calculation or a projection of how much data you need to take and how sensitive we would be given the data that we can take in a reasonable amount of time. And that projection showed that we would be sensitive with very high significance, 5 sigma, the standard definition of high significance in the field, if the background level, if the signal was between 15 and 20%, or the background level was between 80 and 85% of the signal. So we would be sensitive up to a certain level of signal over background inside of our measures. Okay, so now moving away from our history, let's talk about precision, and how we would actually meet those precision goals on the previous slide. A large data set, of course, is needed to hit the small statistical uncertainty target. Again, we're trying to measure differences between the ruthenium and zirconium at the few percent level, so we need a very small statistical uncertainty on our measures. But beyond statistics, systematic uncertainties between the species need to be controlled below the statistical levels. And so because of that, the special conditions that Jim just talked about were come up with in order to keep those systematic uncertainties low. Basically taking a look at what in past runs had caused time dependence or condition dependence to these measures, and controlling those so that they were basically exactly the same between the two species. Now, as I'll show later on in the talk, the precision target that we had in order to make the projected level of measurement has been achieved. A precision down to 0.4% is achieved as anticipated in the relative magnitude of the pertinent observables between the two isobar systems. Now let's move towards the measurements. Because it's a blind analysis, we wanted to make sure that prior to the unblinding and prior to the analysis, that our signatures for what would actually constitute a signature that there's a chiromagnetic effect is there are predefined, right? And they were defined as a significant excess of these CME sensitive observables in ruthenium over those in zirconium collisions owing to a larger magnetic field. There were 5 institutional groups within the collaboration that performed blind analyses of the isobars. Each group focused on a specific analysis method. There's substantial overlap of some analyses between the groups, which helped to cross-check results. All the analyses have a common set of variations for the purpose of systematic uncertainty determination. But because of different detector requirements, there are a set of common and also analysis-specific QA cuts and selections of regions of the data sample with stable detector performance. And again, for each observable and approach, we predefined a set of the CME signatures prior to the analysis for which a high significance must be observed. Okay, let's move to centrality and geometry, right? So one of the major things that we have to do, and the idea behind the isobar collisions was to control the geometry between the two systems. In terms of controlling geometry, we did a classic technique of fitting the multiplicity distribution to Glauber calculations using various Wood-Saxon parameters. Because we wanted to do this, we wanted to define this early, and because we wanted to make sure that it was only based on results from the literature, we used 3 sets of Wood-Saxon parameters from the literature, and we investigated those. The parameters are shown in the table here. We fit to the multiplicity distributions using a 2-component nucleon-based Monte Carlo. That was our choice. And we found that there was a best fit to the data from the case 3. And that's shown most clearly in this central plot. This is the multiplicity distribution for ruthenium, zirconium. The data is in gray, and the red and blue are the various Glaubers. But you can see clearly the difference between the Glaubers in this central plot, which is the ratio of the multiplicity distributions between ruthenium and zirconium. Again, the gray is the data, and the blue here, or the red, are from the Glauber. And you can see that case 3 gets the basic S shape that's seen in the data. the difference in the multiplicity distribution that the data shows. Now, there is potential for further improvement of this centrality determination. We could allow many of these Wood-Saxon parameters to be free and basically try to fit the data better. We could do a better treatment of integers, because when you're talking about multiplicities of 100 versus 101 is actually pretty significant. That's a 1% difference in multiplicity. And we also could think about different treatments of subnucleonic fluctuations instead of using a 2-component nucleon-based Monte Carlo. But that's a future post-blinding improvement that could be there. The result from this procedure is that there's a difference at the few percent level between isobars at matching centrality. Okay, flow and flow harmonic V2. That what's shown on the left is V2 for various 2-particle correlation methods and event plane methods of getting the second order flow, elliptic flow, V2 for ruthenium and zirconium as a function of centrality. You can see that there are different results for V2, especially once you get towards peripheral collisions. Potentially that's due to pseudo-rapidity dependence of non-flow, decorrelations, and flow fluctuations. However, if you take the ratio between ruthenium and zirconium, that's shown here for the 2-particle correlations, and here for the 4-particle correlations in the ZDC, that the ratios for the 2-particle correlation, like V2s, all fall on a common curve. Despite the fact that they're quite different, the ratio between ruthenium and zirconium is very similar. But it's also a few percent away from unity. So there are differences in V2 between ruthenium and zirconium, again, on the few percent level. So this leads to another line in the abstract that observed differences in the multiplicity and flow harmonics and matching centrality indicate that the magnitude of the CME background is different between the 2 species. Okay. Okay, let's now turn to the results of the actual correlators. Okay, so what's shown here are results from one of the groups, group 1, where they used full TPC event plane in order to maximize the precision. We did test, and there's more information in the paper about how sensitive or not we were to various changes or variations in the pseudo-rapidity gap between the particles of interest. Okay, and we saw that these results are insensitive. In any case, you'll see many figures like this throughout the next slides. Let me walk you through the basic structure of these figures. On the horizontal axis is the centrality. On the upper figure is the quantity separately for ruthenium and zirconium, where ruthenium is in solid and zirconium is open symbols. And on the bottom is the ratio between ruthenium and zirconium, along with a fit or an average over the region from 20 to 50% in centrality. We chose beforehand that 20 to 50% in centrality would be our best place for sensitivity from some considerations about potential differences in geometry, that those would be minimal in the region between 20 and 50%. And also because that's the region where our reaction plane resolution and our efficiency, our trigger efficiency for the multiplicity distributions is quite robust. Okay, but what you can see from this fit, if you just look at the numbers, is that the anticipated precision down to 0.4%, if you take the statistical plus the systematic, has been achieved. So we had pushed for 0.4%. We achieved 0.4%. You can also see that in quantities like this delta-delta, which is only a 2-particle correlation, that the precision is quite a bit higher, right? But neither of these were actually declared as a CME signature. Let's start looking at CME signatures. Okay, the first CME signature comes from group 1. This is a quantity called kappa 112. This is, you basically take the delta gamma and then you normalize it by V2 in the delta-delta correlation that was shown on the previous slide. Normalization was motivated by the structure of the coupling of V2 and delta-delta in the background contributions. Again, I point you to the paper for more discussion and also to the literature for more discussion behind that. The predefined CME signature was that this ratio between ruthenium and zirconium should be greater than 1. The result is here. It is not seen. So in this analysis, or in this specific variable, no CME signature that satisfies the predefined criteria has been observed. Okay. So group 2, this group looked at some mixed harmonics. There are 3 criteria here. Is that the delta gamma 112 over V2, the ratio between delta gamma and V2 should be larger in ruthenium than in zirconium. Another criteria is that it should be larger than this 123, where 123 is defined here. It's basically supposed to serve as a data-driven baseline, or something that's not sensitive to the CME, and potentially has the same correlation structure, and is motivated because the third order event plane is not correlated with magnetic field, and also that similar to the kappa discussion on the previous slide, that this delta gamma over V2 should be greater than the difference in the delta delta. Again, the results are shown here for delta gamma over V2, for delta gamma 123 over V3, and for delta delta, and none of these predefined CME signatures were seen. So no CME signature that satisfies the predefined criteria has been observed. That was using the full TPC. There's also a new detector in STAR for this data set that allows us to push to a larger pseudorapidity. As you saw before in the V2s, pseudorapidity does matter to some level in these flow phenomena. And so this EPD, this new detector, provides a large pseudorapidity dependence between the charged particles and the event planes. Again, you've got delta gamma 112 over V2 using the EPD as an event plane, 123 over V3 using the EPD as an event plane. The predefined CME signatures are the same as on the previous slide. You look at the results in the ratio. No CME signature in this analysis that satisfies the predefined criteria has been observed. Okay, another analysis that was done is on this so-called K variable. It's similar to the kappa variable, but it's slightly different, and it also allows for a comparison using the third order event plane. It's defined here. Again, I point the audience to the paper and to the literature for more explanation of that. Again, on the upper part, there's the K2. There's the K3 in the second part. The predefined CME signature is the K2. The ratio of K2 in ruthenium between ruthenium and zirconium should be greater than the ratio of K3 between ruthenium and zirconium. That's not seen in this analysis, and so no CME signature that satisfies the predefined criteria is observed. Okay, group 3 went a little bit differently. They looked at quantities differential in the invariant mass between the two particles. This is motivated by by the structure in the invariant mass, which is related to various resonance structures, and the fact that the main background of the delta gamma correlator is related to flowing clusters. This is just the counting and the ratio between ruthenium and zirconium of this invariant mass distribution. This is delta gamma as a function of invariant mass. And the predefined signature is that basically delta gamma over V2 in ruthenium should be larger than delta gamma over V2 in zirconium. Looking at the result, as a function of invariant mass, you can see that this predefined CME signature is not seen. So again, in this analysis, no CME signature that satisfies the predefined criteria has been observed. Okay, group 4 decided to do a direct calculation of delta gamma over V2. This is a direct calculation which cancels the reaction plane resolution and reduces the systematics as defined here. Their predefined CME signature is that the delta gamma over V2 in ruthenium should be larger than that in zirconium. Again, if you look at this as a function of centrality, nowhere as a function of centrality is this predefined CME signature seen. And so again, no CME signature that satisfies the predefined criteria is observed. You can pause here now to look at the consistency of the results. What's shown here is delta gamma over V2 for the full TPC among measurements made by groups 1, 2, and 3. And on the bottom is something which has an eta gap between the two particles of interest between groups 2, 3, and 4. So the measurements of the similar quantities between the two groups are similar. The statistical uncertainties are largely, but not completely, correlated among the different groups. And the results are not identical because because they're analysis-specific event site selection criteria and slightly different methods. We verified that the results are consistent within the fluctuations due to those differences. The predefined CME signatures, the delta gamma over V2 in ruthenium should be larger than that in zirconium. And as you can see, that is not seen. So again, no CME signature that satisfies the predefined criteria has been observed. Group 5 took a somewhat different tack in terms of their variable. They looked at ratios of distributions of charge imbalance, both across the reaction plane and perpendicular to the reaction plane. It's defined here. I suggest to the audience, or that for more details, you should look at the paper and the many places of literature about this R variable. The predefined CME signature is that the inverse width of the ruthenium should be larger than that than the inverse width in zirconium of this R variable, and that's shown in this plot F. And again, the predefined CME signature is not seen. So no CME signature that satisfies the predefined criteria is seen. So compiling the results, this is a compilation plot which shows basically delta gamma over V2 for a number of different analyses. The kappa 112 and K2 for different analyses, and the R variable. And then, for comparison, the quantities that involve the third order reaction plane. Again, the predefined signature is that that ratios involving psi2 should be greater than 1, and they should also be greater than those involving psi3. And none of these predefined CME signatures are observed. I should note that there are other measurements in the paper that I don't have time to show in this talk. They all have very similar conclusions. So to conclude, we report an experimental test of the CME by blind analysis of a large set of collisions at a nucleon center of mass square root of S of 200 GeV taken in 2018. Backgrounds are reduced using the differences in observables between the collision systems. Criteria for a positive CME observation are predefined prior to the blind analysis as a significant excess of the CME sensitive observables in ruthenium, collisions over those in zirconium collisions. Consistent results are obtained by the 5 independent groups in this blind analysis. A precision down to 0.4% is achieved as anticipated in the relative magnitude of the observables between the 2 isobar systems. There are observed differences in the multiplicity and flow harmonics at the matching centrality. And these indicate that the magnitude of the CME background is different between the 2 species, but no CME signature that satisfies the predefined criteria has been observed in this blind analysis. Now, there's some considerations, some post-blinding considerations that came up after we've unblinded. We deliberately have kept this discussion minimal because we said that we would, unblind the data, publish the data, and then send it to the community. But we thought that it was worthwhile to point these considerations out. The baseline against which to compare the data as documented in the blind analysis was unity, right? And it's not at all clear that is really the proper baseline under these conditions of different multiplicities and different V2s as seen in the differences between ruthenium and zirconium. The proper baseline may be the ratio of inverse multiplicities, or as an alternative, this R ratio where you've got where you look at the pair differences in the invariant mass. So we produced this final plot for the paper where we put the ratio of the multiplicities and the ratio of R on the same slide, and you can see that they are also below unity. In any case, that's only a general guideline. I think we believe that that there needs to be more work in the community to understand how to take into account these differences that are seen between ruthenium and zirconium in order to produce a real baseline. So in other words, the observed multiplicity difference between the isobars requires future study to better understand the baselines in order to best utilize the precision of this analysis. We have 0.4% precision, but as you can see, we're not driven in terms of the conclusions of this analysis by that precision currently. We're driven by the precision of the baseline. Okay, so with that said, I'd just like to acknowledge that this is a huge effort from many people and many institutions. The RIC operations group, the RIC computing facility, which came in order to really help us analyze this data in a timely fashion. Oak Ridge, which provided the ruthenium, and RICAN, which provided the zirconium technical help in order to have the zirconium source. Thank you.
Thank you, Jamie, for walking us through all these results. So, and thanks again also, of course, to Dima and Jim for the 2 talks preceding this. So before we go to questions, I do just want to say again, the paper, and Jamie, correct me if I'm wrong, the paper will appear on the archive tonight at 8 o'clock and will be available until then on the STAR website. I don't know if you want to say any more about that.
Yeah. No, that's a correct statement. It has been submitted to the archive. It will appear at 8 o'clock Eastern time. I guess that's midnight GMT. And it will be on the STAR website.
Okay, then we'll go to questions. So as we often do in the Zoom world, please use the reactions to raise your hand and we'll just go through in the order that we see them in the queue. So the first one I see, I'm not sure who it is, but it's MYG iPhone 6S. So please introduce yourself and ask your question. Okay, maybe we'll come back to that one. So we'll go to the next that I see in the queue. So Dmitry Denisov, please.
Thank you. So I'm Dmitry Denisov. I'm a scientist here at Brookhaven National Lab. So first, Jamie, thank you for a very nice talk. And of course, congratulations to the STAR collaboration. So my question is about these predefined criteria, which you sort of showed. Like in most cases, it's just ratio more than 1 or similar. So what could you really predict this ratio better? Let's say it should be within 10% more than one, or because just having it's more than one is very generic.
I mean, again, the consideration that we had was that, you know, the reason why we were pushing for the precision of 0.4% was that if the chiromagnetic effect was up to, say, 20% of the measure in delta gamma, then we would expect 2% above 1, and so we need a 5 sigma measurement in order to measure that.
Okay.
That was the reasoning behind it. So it was few percent level.
Mm-hmm. So
And
it's similar.
that's the reason why we pushed for the 0.4% precision. But as you can see, you know, the differences in multiplicity and the differences in V2 between the systems are also on that same level, right? It's unexpectedly large. And so because of that, we need the community to help us to interpret that, the right
Thank you.
baseline.
Thank you. So the next that I see in my queue is Krishna Rajagopal.
Yes, hello, this is Krishna Rajagopal from MIT. First of all, enormous congratulations to STAR, to Rick, to the huge cast of characters who've made this possible. It's I think a very impressive analysis and unique in our field to this point. So my question is to the theorists. I guess Dima was the one who spoke, but to Dima or anyone else, all of us were wondering whether, because of the greater magnetic field in ruthenium, there would be, for any of these observables, ruthenium above zirconium because of the greater magnetic field. Did anyone from the theory side in advance consider reasons why ruthenium might be below zirconium? And I'm emphasizing the word in advance. So that's a question to Dima or any of the other theorists who might.
Oh, I certainly did not anticipate ruthenium being below zirconium. And in fact, it's somewhat puzzling because, let's say, I would not be surprised by seeing ruthenium equal to zirconium. It would just mean the signal is too small. But to see systematically ruthenium below zirconium, I think is a real surprise for me personally, at least, you know, in this first moments of learning about the results of this impressive analysis.
Yeah, so I'll say with much less information on my side than on Dima's side, it's a surprise to me also. And so I think there's something very interesting here to understand. The main thing I said at the first, which is huge congratulations to Star and Rick and everyone behind this analysis.
Yeah, I would just add that, let's say, the fact that it's below 1 systematically, I think it's extremely interesting and extremely puzzling. And we certainly, you know, theory community will really have to think hard about it.
So the next hand I see in the queue is Jin Feng.
Hello. Yeah. First of all, again, also congratulations to our STAR colleague for completing such a great effort. And I think that's very helpful for the field and for especially for those of us who are interested in finding the CME. I do have a comment and a couple questions. The comment is about this delta result. If you look at delta, I should point out that if you look at delta, it's actually consistent with the possible CME signal there, because we showed before for the delta correlator, the magnetic field or CME contribution will make the ruthenium to be less than the zirconium in the delta correlator. So that's just a remark. And that was in our paper, for example. Even though delta gamma, so our prediction was like delta gamma should be larger in ruthenium, or delta should be smaller in zirconium. I just want to point this out. Okay, and then here are a couple questions. I think the fact that the two, the ruthenium and zirconium will have different systematics was known, of course, well before the the results. I think, for example, people like Fu Qiang pointed this out, and at Quark Matter 18, we in my talk I specifically discussed this, and we suggest that the better way to analyze is to apply a joint cut of both elliptic flow and multiplicity to make sure you have exactly identical bulk sample from both systems. I understand that the blind system, blind analysis has its own rules, so that no adjustment should be made. I just wonder if STAR has any plan to carry on and, for example, perform analysis along the line that we suggested before. So that's my first question. And my second question is that from your point of view, should the baseline be below 1 or above? Because I don't know the quantitative number yet. I guess V2 over N, V2 over multiplicity would be a reasonable baseline. Would that be somehow just around the this ratio, like 0.97?
Yeah, I mean, on the second question, the first answer is that if you were the naive scaling with multiplicity is the reason why we placed the inverse multiplicity on the same plot here. So that's the naive baseline. You know, if everything is the same and you just have slightly different multiplicity, the naive baseline difference that you expect is given by the multiplicity here, and that's why we placed that on the plot. On the first discussion, you know, trying to do a joint selection on multiplicity and V2, that's a great thing that potentially STAR will do. It was not documented, and so we just couldn't do it. But this is a beautiful data set with, you know, exquisite systematic control that is available for many, many future analyses that could dive into, you know, doing things like you suggested in detail.
Okay, thank you.
Up next is Edward Churiak.
Okay, hi everybody. Somehow you don't see me, but it doesn't matter. So in order to check CME effect, we need to, of course, it has several ingredients. One ingredient is topological fluctuations, which create this balance between left and right. The second ingredient is magnetic field. How magnetic fields stay from initial time to in the quark-gluon plasma. I want to say about the first one. It was assumed that certain number of topological fluctuation happen and on the event basis. So this production of topological object is called Faleron transition, and it gives 6 units of chirality in the fireball. It was assumed that there are of the order of 20 or maybe 10 such events per collision, and from that we calculated chiral imbalance. I want just to comment that with Ismail Zahed, we proposed some time ago, and it was again discussed for in connection with LHC, PP collisions in which we want to observe one single topological cluster, one single Faleron transition. It can be done in diffractive mode, it can be done without diffraction. That would be some cluster of few GeV, like free GeV mass, decaying in a particular way, and it would signify a chiral imbalance event. So maybe there is something wrong with assumptions about topological fluctuations. We can check it separately. I have nothing to say about magnetic field. That would be separate, not experiment, but some study of PP data, maybe, on that subject. That's comment.
I don't know, do any of the speakers wish to respond? Or just take it as a
No,
comment?
just thank you for the comment. It's an interesting thing to look into.
So I do not see any more hands in my queue, but if I'm missing somebody, of course, please speak up. And of course, there's a lively discussion going on in the chat that I see.
Yeah, the chat, we're supposed to follow it. Or?
There's a good discussion going on, is all I can say.
Why people don't speak to everyone?
Here, now we've got another hand. So Jin Yang, when you're ready.
Yes, I'm just maybe I put a lot of comment on the chat. Maybe I just want to comment. And let me first of all congratulations to STAR colleagues. And I think this is the first time I've seen that such a measurement with such precision has been made in the heavy ion environment. And that, of course, to see the EMC, now we have to really go beyond the so-called predefined criteria now to see whether there is an effect much maybe smaller than we anticipated. And then the next stage, I think, maybe to understand, you should beautifully that there's still a difference in multiplicity distribution between the two systems, which means that the two systems, even in the initial geometry, as I think Fu Chan and his colleagues has published before, are still somewhat different. And then maybe we can, understand quantitatively that difference, and then its consequences on the predefined signature of EMC effect.
Again, if any of the speakers want to respond or just it's a comment.
Yeah, no, I just want to wholeheartedly agree with that. I mean, I think that the best possible scenario is that we have some calculation that can reproduce the multiplicity difference between the systems. They can reproduce the V2 difference between the systems. There's also V3 results in the paper, the V3 difference between the systems, and use that calculation as a way to define what the baseline should be, rather than doing just naive scaling. That's the reason why we stopped at just placing the multiplicity on the same plot as the results and not just scaling with the multiplicity.
Are those detailed analysis to be included in the paper now, or you have to follow up a paper?
Which detailed analyses? We have.
We were
V2,
talking about the difference between.
We have the paper includes the multiplicity distribution. The paper includes V2 measurements, and the paper includes V3 measurements. So they're all available to the community.
I see.
In pretty strong detail with very high precision, because all of these things have essentially infinite statistical precision.
Yeah.
So next hand in the queue is Bernd Mueller.
Yeah, thank you. I don't want to comment on the physics results. I think they speak for themselves very clearly. But what I would like to do is to congratulate the STAR collaboration to these fantastic, very impressive undertaking and meeting the expectations. But I would also like to point out once more that this result was also based on a heroic effort by the Collider department at Brookhaven to actually accelerate and produce this fantastic statistics that exceeded the original expectations by a multiple factor. And also the DOE, which went all out to produce the isobars that were needed for that particular round. So I think it's a tremendous overall success, not only for the field, for the STAR collaboration, but also for Brookhaven National Lab and for the Office of Nuclear Physics at DOE. And congratulations.
Again, I don't know if the speakers want to respond. I'm sure they want to very wholeheartedly agree with that comment.
Thank you, Baron. I wholeheartedly agree.
So again, I do not see any more hands in the queue, but let's pause a minute in case someone has a question or in case I'm missing someone. All right, not seeing any more questions. Of course, there's still a lively chat going on, which should be viewable in the recording, I think. So if there's nothing else, then thank you again. Thank you to Dima. Thank you to Jim. Thank you to Jamie. And we'll close the seminar.